Hello friends, I Gaurav Morghare. Today I am going to discuss the topic of Z transform. This is an important topic for the subject signal and system and digital signal processing. Our lecture will going to be having the following parameters: the introduction, Z transform, zeros and poles in the first lecture. In the second lecture we'll be going to discuss about the region of convergence, some important Z transform parameters, and in the third lecture we'll be going to discuss about the inverse Z transform, their theorems, and above system function. So in today's lecture we'll start with the introduction about the Z transform. We relate the Z transform with the Fourier transform. As we know, the Fourier transform is used to convert any time domain signal into the frequency domain. For any continuous signal, we'll use the Fourier transform. It is a mathematical tool. And for any discrete signal, we'll use the discrete Fourier transform. Their working or the concept is same. The only difference is of the multiplication factor or the formula which will be used. Normally, the Fourier transform does not converge for all the sequences. That means all types of signals which are not converging to a point, that means which are not a finite. We know that there are the limitations of the Fourier transform. The Dirichlet's criteria clearly defines this. The Dirichlet's criteria says it is difficult to calculate the Fourier transform for any signal if it does not contain the finite number of maximas and minimas. That means if a signal is constant, then it is very difficult to calculate the Fourier transform for that signal. And the formula for the Fourier transform is integration minus infinite to plus infinite ft, which is any signal, into e raised to the power minus j omega t. That should be the that should be always finite. So where the Fourier transform is limitation that it does not converge to all the sequences, so Z transform can easily calculate for all these signals. But the only difference is that the Z transform convert any time domain signal into the Z domain. It is normally used for any discrete signal. It has a very good analysis or the notation, and some complex variable theory also comes when we deal with the discrete time signals and systems. So the definition of the Z transform is simply defined by this formula. As you all see, the xz, normally it is the representation. Xn is any signal which is the discrete time signal. The representation for any time domain signal starts with the small x, and the n gives the discrete value of the times. Summation n is equal to minus infinite to plus infinite and z to the power minus n. This is an multiplication factor. Similarly, for the Fourier transform, the discrete Fourier transform will say the formula is the same, only the multiplication factor, which is z to the power minus n, is changed into e to the power minus j omega n. Only this is difference for the formula, although the concepts will discuss it later on. So as we know, the Z transform will convert any time domain signal into the Z domain. So what is the Z domain? Z domain here clearly shows a Z plane. This is having a real axis and an imaginary axis, and the distance is normally shows by the frequency omega if we are going to use this discrete Fourier transform formula. And this distance or the radius, which we usually call, is depend upon the value of the Z. Further, the concept of the ROC, or this topic will be elaborated with the concept of ROC, where it will be clearly defines what is the value and how our system will be stable for that. So for the Fourier transform is used to evaluate the Z transform of any unit circle. This is the three-dimension representation of any Z plane. It clearly defines as that we'll be having a real axis, an imaginary axis, and the vertical Z axis over which the Z plane is lie. For the properties of the Fourier transform, it's just simple that the Fourier transform should have the periodicity property. What is the periodicity property? That's a simple thing. We're going to take any sinusoidal signal or cosinusoidal signal which is having a time period of 2 pi. So it clearly defines as the Fourier transform is periodic function with the period of 2 pi, as the signal is starting from the minus pi to plus pi, and after that its value is repeating itself. Concepts of zeros and poles. So concepts of zeros and poles is just simple. We'll start with the Z transform concept. As I told you, the region of convergence is the simple thing that those set of values of Z for which the x of Z is finite is defined as the region of convergence. Similarly, as we know that our formula for the Z transform is x and z to the power minus n from the summation n is equal to minus infinite to plus infinite. That function or the factor should be lesser than infinite. That means it should be a bounded. So ROC is nothing but a centered on an origin, and it consists of the rings which is dependent on the value of z. This is an example. If the value of z for which the xz is finite is variable from value of rx minus to rx plus, so there will be a two concentric circle. This small circle is having the radius of rx minus, and this is the having the radius of rx. As we know that rx plus, the value of z is lesser than rx plus, that means this is rx plus and the value is lesser than, but it is greater than rx minus. That means the shaded portion is showing the region of convergence, and for this value our system is stable. If we show the relationship between the Fourier transform and the Z transform, it's just a simple representation that if we'll substitute the value of Z is equal to R into e to the power j omega, it will be clearly indicate the relationship. The ROC concept is almost same for the Z transform. Now we will describe about the stable system. From the concept of ROC, as we know that if this is an absolutely signal which having a finite output for the values of z, then the system is said to be the stable. But the input, whatever we are applying, should be finite. So for any stable system, it's the definition is very clear. We have to give bounded input, and for the bounded, that means finite input, it will going to give us a bounded output, that means the finite output. So the Fourier transform is to evaluate the Z transform of a unit circle, and the stable system, that means their ROC should be defined very well. This is an example of any right side sequence. That means what the output or the signal is lying from right hand side of the origin, that means positive value of time from 0 to. Similarly, if we'll see, if we'll have to calculate any signal which having the value of e to the power n un. Un is the unit step function which is having the value of 0 to infinite, having the magnitude of 1. It does not lie for the negative value of time. If we multiply it with the factor e to the power n, if un is multiplied, then the limit will be always 0 to infinite. It is clearly seen in this formula. A to the power n is the exponential function. As we know that values of a, if values of a is lesser than 1, then it will be decaying exponential, and if the value of a is greater than 1, then it will be going to give us a rising exponential. So in this step, it is easily calculated that if a to the power n un is calculated for the Z transform, the answer will be z upon z minus a, and ROC will be mod of z is greater than a. This is an stable system. Only the value mod of z, that means the z should not be equal to it, that should be always greater than equal to a. For the left-handed sequence, here the sequence is minus a to the power n u of n minus 1, then it will going to same value, but only the difference is a mod of z is lesser than a. This is not a stable system. Thank you for the lecture. In the next topic, we are going to discuss about the ROC.